Okay, so welcome back everyone. Again, this is INF721, deep learning, and today we're going to talk about machine learning. And before we do that, actually, I have a couple of announcements. We have a Google Spaces set up for the course, so if you're not there yet, please let me know after the class. I've added a bunch of people who are not officially enrolled yet, but there were too many people emailing me. It's hard to keep track of who actually I already added or who I didn't. So please let me know if you are not in our Google Spaces yet. And the lecture one is already available on the course webpage. I can show it to you later if you haven't found it yet. I can show it again, but maybe just let's leave it to the end of the lecture. And last time we talked about motivation for neural networks, machine learning, and some core syllabus. Unfortunately, we stopped a little bit earlier last time because my laptop ran out of battery. But what I planned for today was, well, actually finish what we started last time, which was an introduction to machine learning. But I want to extend that a little bit to talk about supervised learning, which is the main kinds of problems we're going to tackle in this course. That's where actually these kind of problems called supervised learning problems, there are the problems where machine learning succeeds the most, sorry. So that's why we're going to mainly talk about it throughout the whole course, even though we're going to talk about other stuff as well, like unsupervised problems. And we're not going to talk about reinforcement learning because it's considerably different. So we won't have time for that. But so regarding supervised learning, I want to talk about or define more formally what it is that we call hypothesis space, loss functions, and how we evaluate performance of such models. And then I want to start actually with our first algorithm, which is linear regression. In fact, linear regression is a classic method from statistics, but it's a basic building block for neural networks. So we will see that the moment we talk about the first neuron, we will see that actually there's going to be a linear part in our neuron as well that very much looks like a linear regression. So any questions before we start? Okay. So machine learning, right? We were talking about this last time, so I'm just going to go very quickly. We were discussing that AI is this field of computer science and other related areas that is interested at building computer systems that can simulate human intelligent abilities, like learning, reasoning, planning, creativity, and others. And then within the field of AI, there is a subfield called machine learning, where we are interested in learning to perform tasks from previous experiences. In other words, we are interested in creating computer programs that can perform tasks or solve computational problems without being explicitly programmed to do so. And, well, deep learning is a class of algorithms based on neural networks that are a method for doing machine learning. And particularly these neural networks are models inspired by the actual biological brains of neurons in our brains, okay? As I said, I'm not going to talk much about this connection to the biological brains, but in fact there is this relationship from the theoretical side of neural networks. Okay, and then we stopped right here, actually. I was briefly talking a little bit about the history of machine learning and AI, and So just a quick recap, in the 40s, that's when we can say that machine learning started, because we have McCulloch and Pitts designing the first electronic neurons. So they were not, you can't probably read there, but it says that there were adjustable weights, but they were not learned, right? And then in the 50s, mainly Rosenblatt here and others designed the perceptron, which was actually an algorithm to learn the weights of a neuron. So now, by this time, we can actually train a neuron to solve a particular task. And the kinds of problems you could solve with the perceptron are called linear problems, because the perceptrons, they could only separate a space with a hyperplane. We're going to talk about this. Basically, when you have a linear problem, you can think of something like this. You have, for example, a binary classification problem can be a linear problem if there is a line, or in a high-dimensional space, if there is a hyperplane that separates these two classes of examples. So we call these kind of problems linear problems, because there is a line that separates the data. But some problems might not be linearly separable, and this kind of problems the perceptron couldn't solve, right? And that's what Minsky here showed with a very simple example of the XOR problem. We can draw the XOR function like this. There isn't a single line that separates these examples for the XOR problem. So there was a paper here that actually started criticizing this theory behind the perceptron, and from that time on, you can see there was an AI winter, because people started not believing on this solution that much. Because, well, if they can't solve such a simple problem, right, what can we do with this, right? But then from the 80s on, we had some evolution or some advance in the field with the multi-layer perceptrons and the backpropagation algorithm. So with that, then this kind of non-linearly separable problems like the XOR, they could be solved with these more complex neural networks with multiple layers. Still, from that time on, at the same time, not at the same time, but like around the 2000s, another very effective and important algorithm came out, the SVM, which is the support vector machine, which is designed for linearly separable problems, but there is a trick you can do to solve non-linearly separable problems, which is called the kernel trick. And what was cool about the SVM is that it has a lot of theoretical guarantees, as opposed to the neural networks at that time. They didn't have much theoretical guarantees. More specifically, the SVM was shown to be a convex optimization problem. And we're going to talk more about this in this class. So it became very popular algorithm to solve many different machine learning problems. But then, since the 2010, there were many important advances in the field of neural networks that reflected on what we see today. So I didn't have this figure, so I made this figure myself just to show a bunch of important advances that happened in the last 14 years that allowed us to have what we have today. And this is not even close to the amount of new discoveries we had. It's just like some major points or some major discoveries and new algorithms that we have. Obviously, there's many more. But you can see that every year there was, since 2010, 2012 here specifically, every year there were a lot of cool innovation going on. So for example, in 2012 here, this is the year that people normally say that this is when deep learning really kicked off. Because of this paper here, or this network called AlexNet, which was designed to solve an image classification problem on the ImageNet data set, which is a data set with millions of images, and there is images of 1,000 classes. So there were competition around this data set, so which was a very hard challenge to solve for many, many years. And in 2012, AlexNet beat the other algorithms by a lot. I don't remember exactly the percentage, but it was something around 20 or 15%, which was a lot at that time. I really recommend reading this paper because it's kind of now a foundational stone for who is starting on deep learning. There's a lot of cool things happening here. First of all, the size of the network all of a sudden became much bigger than it used to be at that time. Now we have nowadays in 2024, we have actually much, much bigger networks. But at that time, AlexNet was huge. And there were a bunch of cool stuff happening there that we still use to this day. For example, they trained their network using GPUs. They used ReLU activation functions. So they combined a bunch of cool stuff that wasn't very popular before then. And then it really proved to be an effective solution. And that instigated people from other fields to start using deep learning. Because the results are so cool that, well, what else can we do with this, right? And then this influenced natural language processing people to solve NLP with deep learning approaches, and all others also started doing that. But then, let's say 2013, we had variational autoencoders, which is like a very nice, very cool generative model. And then we have the deep QN, which is one of the foundational ideas for doing deep reinforcement learning. And this paper came out also shown to very, very, very interesting and promising results around deep reinforcement learning. We also had Word2Vec, which is a model we're going to study in this course for representing words with vectors. 2014, we had GANs and the Adam optimizer. 2015, batch normalization. 2016, we had AlphaGo, which is also insane result from AI from the previous 10 years. AlphaGo beat the best player at Go, which is a gigantic game, much bigger than chess. And also we had YOLO, which is one of the most famous computer vision algorithms of the same year. And then 2017, we had transformers, also a huge revolution. We use this as our major network nowadays. And then from 2018 on, we had this GPT project started and actually being developed over the years. So 19, we had GPT-2, and then GPT-3 in 2020. Also, another cool invention, which was diffusion models. And then 2021, CLIP, which also started allowing us to do multimodal learning. And then image generation models actually became very popular in 2022. All the major companies nowadays have their image generators. And last year, we started seeing this boom of large language models, also different big tech companies having their own chat-based or prompt-based large language model. And since this year, now this has increased to have multimodal capabilities. So now the large language models understand image and audio very well. So this is just to show that every year we've been getting crazy amounts of new inventions, and we don't know when this is going to stop. In fact, deep learning is one of the most important scientific areas these days, right? If you look at, I like to show this. Let me see if I can show you quick. So if you look at the Google Scholar metrics, which measures the kind of the impact of scientific venues, we have Nature, which is the oldest magazine or journal in science. It has like this is H5 index is how we measure impact of a journal or a publication venue, like a conference. And if you look at the second place is CVPR, which is a computer vision conference, which is one of the top conferences we have in computer science and AI, obviously. So if you look at the top 10, we have iClear here, International Conference on Learning Representation, which is a deep learning conference. Neural Information Processing Systems, NeurIPS, is a deep learning conference. So in the top 10, we have 3 actually deep learning conferences. And this is among all sciences, not inside computer science only. So here you can see how actually big is the impact of deep learning in science as a whole. Okay, so let's actually start to work on machine learning. So to start working with machine learning, we need to understand and formalize the problem. So there are different types of machine learning problems, but overall, we can formalize it this way. So we are given a data set D, and I'm going to try to be consistent with my notation throughout the course, but it's hard to be consistent across the slide, so if you get confused about the notation, please let me know. But I'll try to always refer to the data set with the capital letter D. And so given a data set D and a performance metric P, we want to learn a function, age of x. And here, notice that this x here is a little bold, because I'm going to use this notation of bold variables for vectors. Okay? So this is a vector. And we call this function age of x a model. And we want this model age of x to minimize an error on a function. I should have changed this, sorry. When you're optimizing something, you can think of performance that you want to maximize. You can also think about error, which you want to minimize. So let's just think about minimization. And so we have an error metric L, and we want to minimize the error of, when we call L of x prime, which is the application of this metric on x prime, which is unseen examples. So we have already some important components here. We have a data set, we have a loss metric, or an error metric, L, and we have a model. And we want to minimize the error of that model with respect to that metric. But there is a trick here, there's a twist, right? It's not as simple, because we want to minimize the error on examples we have never seen before. In other words, examples that are not inside D. So we can only look inside D to learn this function, but we want to optimize for examples you have never seen before. So let's just visualize this with a diagram. So thinking more pragmatically, if you are working with a machine learning project or on a machine learning problem, your first step is to acquire data. Then this process or this first step would give you a data set D, right? And then with this data set, we would be able to train a model. And normally, when you're training a model, or most machine learning algorithms, if not all of them, are going to have to define a hypothesis space. Sorry, for a hypothesis space, actually all of them have to have. So all of them are going to have to define, what I mean by hypothesis space is the kind of functions you can look for. So the space of functions you can search for. And this is important for any machine learning algorithm. All of them have to do that. But most machine learning algorithms also have an optimization problem built in, and attached to that, they have a loss function. We're going to talk about these components in a minute. But then when you train a model, after doing that, what you have is what we call a learned function, or a learned model. Edge of x, sorry, here there's a typo, there should be, this x here should be bold, like this one, because this is, in this class, in my notation, this should be a scalar, and this is a vector, okay? So I'm going to fix that. Here it's correct. So when you're evaluating your model, you need other examples that you have never seen before, that are not here in D, right? Because think about this, in machine learning we are interested in predicting the future. We are not interested in predicting the examples we already know, right? We want to learn from data. So by learning, I mean I want to use my experience, the experience that I have, to generalize to future experiences. So that's why we always evaluate our models on unseen examples. I'm calling them x prime here. And then when you evaluate, you get a performance L of x. So just to be consistent, I'm going to change this to error. So depending on how your data looks like, we're going to call the problems a little bit different. So we call the type of learning is defined by the type of experience or the type of data you have. So if you have labeled data, we're going to call these supervised learning problems. And I'm going to give you more examples about each one of them. But if you have unlabeled data, then we're going to say this is an unsupervised learning problem. And if your data comes from an environment, and an environment provides you rewards, then we're going to call this reinforcement learning problems. Okay. So let's formalize supervised learning first, because this is the kind of problem we're going to deal the most in this course. And in supervised learning, we have our data set D is composed of tuples x, y. And I'm going to use this notation here, superscript parenthesis I, for denoting the index of the example in the data set. Okay? So if I had, let's say, a data set, it's actually D like this. So the first the x here is a vector. So let's say this would be 0, 1. And the second element of the tuple is a label. Let's imagine it's 0. So this is our first example. Here. This is our first example. A second example could be, I don't know, 5, 2, comma 1. All right. Let's use semicolon here. And a third example could be minus 3, minus 1. Right? And this could be 0 as well. I don't know. And then you would have a bunch of these pairs or tuples where these values here are our x's and these values here are our y's. Okay? So what is important is the x's are vectors and the labels are scalars here. And so the I there that you see on the x and y, the I index here refers to the index of this example in the data set. For example, this first element here has I equals 0. So this one has I equals 1, and so on and so forth. So whenever I say, for example, x1, y1, I mean this pair. If I say only x1, then I mean the feature vector of the first element, which is 5, 2. Okay? So this is the notation I'm using. Is this clear? So formally, we have, we can define our data set with a set, right, of these pairs where this set D is contained in RD cross C. And because we have pairs, right, so we have two domains. The x's are in the RD domain and the y's are in the C domain. So m here, and I'm going to try to be consistent again with this variable, m is the number of examples in the data set. So if you have, let's say, 10 data points, our m is going to be equal to 10. If I had 100 data points, my m is going to be 100. So it's the size of the data set, okay? And when I say data points and examples, I also mean the same thing. Each tuple here, we call it an example. So more formally, x of I is what we call a feature vector of the ith example. And the y of I is the label, sorry, there's a typo there, or class of the ith example. And RD is the set of vectors in the real space with D dimensions. So D is the dimensionality of the feature vector. So if my examples have x's with, in the 3D space, then we're going to say that D is equals to 3, because there's 3 dimensions here, and every example in the data set will have 3 dimensions. In machine learning, it's very common in real world problems, the number of features we have, it's much larger than 3. For example, if you're dealing with the very small images, think of images as 2-dimensional arrays. There is a very famous data set called the MNIST data set. We're going to talk about this. And this is a data set of hand-drawn digits. So, for instance, you could have a 2 there, an image of a 2 that was handwritten by someone. And the images there are 28 by 28 pixels, right? Which is a very small image. But if you think about this, one way to represent this image as a feature vector is to flatten this image and have a vector where the first row is concatenated with the second row and the third row and so on and so forth. So you would have a vector which is 28 by 28 dimensions, which is something about 760 or something. So it's much bigger than 3, right? And if you think about NLP problems, you have to deal with the whole vocabulary of English or Portuguese. And you have, I don't know, like hundreds of thousands of words. And then maybe each dimension here represents a word, and then this is going to be a very, very large vector. So, and in fact, this is a characteristic of machine learning problems that you have to think about very frequently. Okay, and then C is the label space, which is also a set that defines all the labels we can have in our problem. Is this clear? We're going to see some examples now. Okay? So, very common example of machine learning problem is spam detection. So we all have that in our emails. So when Gmail receives a new email, it tries to classify that email as spam or not. And this is a prediction problem. There isn't a function you could write, or maybe there is, but no one knows how to write such a function, at least we are not aware of such a function, that can 100% classify an email as spam or not. So there is a model that predicts whenever that email comes in, is it spam or not. So in this kind of problem, we call it binary classification. So it's classification because we have a finite amount of classes. Our set of C here, which is our label space, only has two values, 0 or 1. So the label of the labels of this problem can only be 0, not spam, or 1, spam. Okay? So because we only have two labels, we call this a binary classification problem. Okay? And one way you could transform an email into a vector, and this is important, this is what we call a representation problem. Right? When we are working with neural networks, our inputs are going to have to be vectors. So when you have an input that doesn't look like a vector, at least at first glance, you have to figure out a way to represent that input as a vector. And one way to do that, and which is a very maybe naive or simple way, is to just count the frequency of words in the email. So we create a vocabulary of words. You can think of every possible word in the dictionary, and you just associate an index to each word. So let's think about the dictionary here. We have the words a, and then ant, and then aunt, and then until like you have all the words with Z here, zoo and Zelda. It's probably the other way around. Right? So you could just index these words and then count the amount or the frequency of each of these words in the email. Right, let's say there's a word here, million, right? And there is one count for that word in that email. And the same for you just got $1 million. Okay. So that would then become a vector, which is an integer vector, but it's a vector, and that could be our feature vector x, for example. We have more interesting ways of doing this, and we're going to talk about them, which is a very important problem within natural language processing, which is how you represent words or documents as vectors. Is this clear? Question.
Does the vector has to be an integer vector?
Now, in this, no, it doesn't have to be integer. It can be real. Actually, we defined it as a real, right? But integers are contained in the real domain, so it's fine, right? It doesn't have to be integer. No, it could be. It has to be a vector. Yeah, it has to be a vector, a list of numbers. Yes. It cannot be like a character here. If you're representing characters, you'd have to transform them into numbers anyway. Another very classic problem, I briefly mentioned it, which is handwritten digits classification. And this is also a classification problem because we have a label space C with a finite number of classes. But now we have 10 possible classes, right? We have 10 digits from 0 to 9, and we want to have a data set full of handwritten images from 0s to 9s. And we want to get an image and classify it as one of these labels. In other words, I want to give an image, and I want to figure out what digit is inside that image. So this is also a classification problem, but this is a multi-class classification problem because there's more than 2 classes. So anything bigger than 2 is a multi-class classification problem, but it has to be finite. Okay. And what is left is the regression problems. And here there's a typo here. There should be house price prediction. And in regression problems, we also have an input vector x, but our labels are real numbers, or any number. So this house price prediction problem is very popular. For example, you want to predict, given the location of a house, let's say I have an apartment in downtown, I want to predict its size, right? So the output is any number, because the number represents a price, and the price can be any number from not minus, but perhaps from 0 to potentially infinite, but let's say at least like millions of reais, right? Or dollars. But then here it's very common to have this problem represented as a table where you would have the first column would be, for example, the size of the house in square meters, and then second column would be the location. And then you could have many other features until you have the label, which is the value or the price. This is our y. And this is our x1, and this is our x2, and so on and so forth. Here you would have prices, let's say, like 105.2, right? Imagine this is in like times 1,000 or something, just so you can write short prices or small values. This is represented in times 10k or something, or maybe just times 1k, 10k, okay, very expensive houses. 105.2, no, times, actually, yeah, 10 times 1,000, yeah, that's what I meant, right? So this would be 5, yeah, something like this. Here it could be 210, maybe there's 5.72, right? And here we have sizes. Let's say if the house is 100 square meters, 200 square meters, and location here could be actually categorical. Here could have like neighborhoods, let's say Centro, or Clélia Bernardes, or something like this. So you could have mixed types of features. That's fine. They could have different scales like this, right? Maybe this here goes from size, maybe goes from 0 to 1,000. Price probably goes from 0 to maybe 1 million, 2 million, who knows. And you could have other maybe features that goes from 0 to 1. So that is all possible. And we call this kind of data structured data because it comes in a table. You can put this in an Excel sheet. And the other examples, we call them unstructured data because you cannot put them in a table, at least not as they are, as they come naturally. Is this clear? Okay.
Lucas,
Yeah?
may I have a question?
Yes.
About images, images are considered structured data or unstructured data?
That's actually an interesting question. Some people say it's structured because it's a two-dimensional array, right? But I prefer to say that structured data is data that fits in a table. Anything else I would call unstructured data. But I've seen people saying that images are structured because they have this two-dimensional array property. But the problem to me is that images can have different sizes. And then you don't, you don't have a structure anymore because you have to deal with that problem. Right? When you have a table, then everything is very well defined. Your feature sizes, so the amount of features you have is going to be the same for every example. You don't have to handle that problem.
Okay, you have a meaning for each feature, right? When you have a table.
Wait, I didn't understand.
Like you have a meaning somehow for each column, and you don't have it on an image, right?
Yes, yes. That's the way I see it. And there's a lot of people that define it this way. But you could actually define what structure means in a different way. But yeah, that's the definition that I think is most useful, at least to me.
Okay, thank you.
Okay, so just to visualize the difference between classification and regression, in classification we have, here is a binary classification problem. We have these examples labeled with green and red, and in classification problems, what we want to do is find, we're going to train a model that can separate this space of examples, right? And then one way to do that would be, for example, to think of a line, and then can we draw a line, or can we draw a plane if it's 3D, or hyperplane if it's it has more dimensions, that splits the data in two, okay? But if you had more classes, then there would be a different color here, and then the problem probably would need a more complicated model, or you'd have to use two lines. Well, it really depends, right? But what we're trying to do with classification is trying to find a function that splits the data, right? And regression, it's slightly different. We want to find a function that fits the data. So the best you can, right? And we're going to see examples, many different examples of each of these problems in this course. Okay, so for now, that's all we're going to talk about supervised learning. Let's switch gears a little bit and talk about unsupervised learning problems. As I said before, in unsupervised learning, the examples in the data set D, they don't have labels. So we don't have actually this column here. Why? Or we don't know the classes. So since we don't know the classes, then the goal here becomes to find some patterns in the data, or somehow understand the structure of the data. So find some hidden patterns or other types of relationships. So classic examples, before that, some formulation. So it's very similar to supervised learning. The difference is that now each example doesn't have a Y or a label associated to it. We only have the feature vectors. So we can't predict the Y because we don't have it. So that actually puts us in a different situation. But the meaning of the X is the same. It's still the feature vector of the ith example. And the domain now here also still is the same. We have D dimensions, and X is a vector defined in the RD space. Examples of unsupervised learning problems. Clustering is one of the most classic examples. And here you have, think of a two-dimensional problem like this. Here we can visually see that there are kind of like groups among these examples, right? But we don't know that. So we can run a clustering algorithm to identify these groups. So these curves here you see in colors, those were learned by an algorithm, okay, based on the distances among these points. So if you say, for example, closest points are somehow in the same group, then we can group them, right? Another classic problem is dimensionality reduction. So as we already briefly talked about, in real world problems, we might have like tens of thousands of features. So the amount of features you have can be extremely large. And that might make it really hard to learn a function. For example, supervised learning. So it's very common that before training a supervised learning algorithm, people would do one step before of dimensionality reduction. So there are algorithms that help you reduce the size of your D. So let's say if you had 100,000 features, there are algorithms that help you identify which of those features are more important. So basically, it tries to find correlations amongst the columns, for example. Think about, say, location and size, right? Intuitively, we can imagine that some neighborhoods have just, in average, larger houses, right? And some other neighborhoods, like downtown, might have very small apartments. So somehow these two columns here are very correlated to each other. So maybe you could just combine them in one, or just drop one, because they inherently they have the same information, right? So you could run dimensionality reductions. These algorithms, they figure this out. They kind of understand which columns are related to which one of them, and then it tells you, okay, you could actually drop this one, and this one, or because they have almost the same meaning, at least for prediction. It wouldn't add much to your, or it wouldn't reduce much your error if you remove this column from your data set. Sorry. There is some, I forgot to translate that, and even actually, I copied this and didn't fill with the right text. And more recently, we have generative AI as another example of unsupervised learning problems. So if you think about image generators, they learn distributions that could generate that example. So you don't have labels. You just have the features. You just have the images, and you find patterns, or you actually learn a distribution that can generate that that examples that are similar to the ones that are inside your given data set. We're going to talk about this at the end of the course. We won't talk much about dimensionality reduction and clustering. Those are normally studied in classic machine learning courses. But we're going to talk about generative AI towards the end of the course. And just to clarify, some people call these new kind of approaches to generative AI also auto-supervised learning. Meaning that these, or self-supervised learning, sorry. Meaning that the models are instructing themselves somehow, right? So there is this also, if you see this name, self-supervised learning, it also relates a lot to generative AI and how these models are trained. It's inherently different than the classic unsupervised learning problems, but it's also unsupervised because there is no label there. Okay, what time is it? It's 5:07, okay. And the third major type of learning problem is reinforcement learning. As I said, we won't talk about this in this course because it has its own ground in theory, which is fairly different. There is another whole set of algorithms involved, and the formulation is slightly different. This topic deserves its own course, And normally you're going to see a little bit about this in AI courses more generally. But in reinforcement learning, we also want to learn a function. The function there is normally notated as pi of s, because we call this pi function a policy, but it's also a function that takes a state s as input and predicts an action. So here we have this idea of an agent. You can think of a cleaning robot, for example, trying to move in the environment. Right? So the robot perceives the environment, receiving a state S, and then it takes an action. So the policy is this function inside the robot that tells the robot what to do next. Reinforcement learning is very common in the context of robotics. But it can also solve other problems. It's also very popular for game AI. So if you want to build an agent that plays a game, reinforcement learning is very effective for that. So it predicts an action A from a state S, but it's also a function. And here, our optimization problem or goal is a little bit different. We want to maximize the expected sum of rewards that is given by the environment. So visually, we can think of an agent, right? And we have an environment, and the agent is in the environment, but it doesn't know the environment. So the environment, so the whole pipeline starts with the environment giving the agent a state at the time t, and also it gives a reward. Sorry, should be, the animation is wrong here. This shouldn't be here at this point. But the environment gives a state to the agent takes an action A at the instant t, and then the environment returns back a new reward at the stage t plus 1 and a new state t plus 1. And then this runs as a loop where the agent takes an action, receives a reward, and it keeps doing that until maybe there is an end state or something that is a special state, like in a game. Right? If you reach the end of the game, then the whole loop stops. Or maybe this could be infinite. Like if there's a robot navigating the moon, right? It might be navigating until it dies or something, right? So it doesn't have to stop. But as an agent, as you iterate with the environment or interact with the environment, sorry, you would get these rewards. So you should learn that you're doing well if you're getting good rewards. Right? If you're receiving bad rewards, you are probably doing bad. So you should learn throughout this interaction. So just to formalize, the agent receives a state and performs an action, and the environment returns a reward every time, and also a next state. But again, this is not for this course, but it's within the subfield of machine learning. So it's important to mention it here. And in fact, there is a lot of advances in deep learning that are designed that are being developed or have been developed to solve or to better solve reinforcement learning problems. Okay? So you have specific neural networks, for example, that have been designed for these kinds of problems. Okay, and finally, we already probably talked about this, which is this idea of data types. Just I want to make this clear. When I say, at least in this course, when I say structured data, I mean tabular data, like this one, for example. This table here for the house price prediction. And this here could be another example for, let's say this is a very common prediction problem as well on the web. Advertisers, they want to know if you're going to click an ad or not. So they know, for example, whenever you enter a web page, there's ads on the web page, but every different user gets a different ad because they run a prediction algorithm to give you the ad that you most likely are going to click. So you can train a model to predict, for example, I have a list of 1,000 ads I could offer you. Right? Which one of them you would click more with more likelihood. Right? So for example, I would have somehow your information, your age, where your state that you are, right? Maybe you have an ID in the system or something. Or anything that can model the user, you could have as a feature. And then your label would be either, it would be a binary problem. Either the user is going to click or not on that ad. Maybe a very important feature here would be the time of the day, right? If it's morning, if it's afternoon, or if it's night, then you click or not, right? It really depends. But this is there. So most companies do something like this nowadays. And unstructured data, which is images, text, and audio. We're going to mainly focus on audio and text in this course. If you have time, we could talk a little bit about audio. Hopefully, there's going to be some example that would nicely fit some class. But most of the advances in deep learning in the last 10 or 15 years were designed around images and text. Because if you think about this, these are perhaps the most basic abilities that humans have, right? We can communicate through language and we can see stuff. So if you manage to solve these problems of vision and communication, that's a big deal. Then you can make very strong AI agents that can see and communicate. Audio is also very important because thinking about speech and understanding actually communication through speech is also very important. But those two have been the focus for a long time. But recently, audio has been also, it has increased a lot, the amount of research around audio, and but it's actually not as close as image and text yet. All right, so from now on, we're going to be, for a long time, talking about supervised learning problems. So whenever I say now machine learning, you can think of actually supervised learning problems. Because most of the problems we're going to talk about are supervised learning problems. So let me just, again, bring back this diagram, now framed as a supervised learning problem. Remember, we want to learn a function, but now our function is a function h of x equals to y. So we want to predict the label y from the feature vector x, right? And we are giving a data set D that has this format here that we already saw. It has m examples. And our goal is to minimize the error L of x prime on unseen examples x prime, okay? Nothing very different here. The only difference I put is, first of all, you have the data set now in this format. We always have labels now. Our function has this shape. We want to predict a label y. And now we are interested in either classification or regression problems, depending on how our labels are in our data set. And we're going to see that there are very common metrics to evaluate these models. For example, for classification, we normally use accuracy or some other similar metric, like precision, recall, or F1 score. We're going to talk about them. But we have very common metrics to measure the performance of classification models, and also for regression. For regression, we can use squared or absolute error. There are also other metrics, but there are many common metrics for each one of these problems. But now we are limited to this scope, which already allows us to solve many different problems. Questions? Okay, so let's move on. That's just that same diagram now with the scope of supervised learning. And so let's think for a moment what it means more formally to say we are training a model. So we've been using actually this expression, training a model, but formally And without actually talking much about in a specific algorithm, when you talk about training a model, we are talking about finding a function edge within a space, capital H, of functions. So we need, or we can imagine, a large space of functions and we want to find a specific function edge inside this space. And it's important to formalize it this way because edge is a set. It could be an infinite set, but it's a set. And I need to define this because otherwise I can't search. If I don't have a formal space to limit the amount of things I can look for, there's no search you could run. So the edge is the space of functions we can look for. And the lowercase edge is one particular function there. And we're going to see an example in a minute. So to train a model, any supervised learning algorithm needs to first define this space. There's a typo there. Defining specific space of functions, and we call this space hypothesis space, H. And then, once you have defined this hypothesis space, now you can somehow search for a specific function inside this space, right? And you want to find the best function, somehow, right? And the way we define which one is the best is through a loss function, which measures the error of that function edge on a data set, for example. We're going to see examples of this. But again, these definitions are really important. And particularly in neural networks and many other machine learning algorithms, step 2 here is formalized as an optimization problem. Which means we have a large set that could be infinite potentially, and we want to find the best function there according to some loss function. So you would have a minimization problem where you want to find the function edge that minimizes the error on a certain data set. A lot of different algorithms have the same or have a similar procedure. So let's see some examples of hypothesis space. So I could define my space edge as the space of all linear functions. So see, this is an infinite set. There's infinite many linear functions. But it's a well-defined space. When I say I'm going to search for linear functions, I'm throwing away quadratic functions. I'm throwing away any other polynomials. I'm throwing away sine functions. I'm throwing away any other function that is not a linear function. But when I define this, now I can search. Because I have two specific parameters here, W1 and W0, that I can somehow tune to minimize error. Now I have a formal representation. Right? So this is mandatory. Any algorithm has to do that. So for those of you who have seen other algorithms like decision trees are the same. They limit the space to trees. So any function that can be represented by a decision tree. And any other, like logistic regression also has a hypothesis space. Neural networks have a hypothesis space. Naive Bayes has a hypothesis space. Any algorithm has a hypothesis space. Right? You could define it differently. For example, you could say, I'm going to search for sinusoidal functions like this. Again, it's an infinite space, but it's different than this space. Okay. And I don't know, you could search for all the 12-degree polynomials, and I put this here because if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points, you can perfectly fit these points with a 12-degree polynomial. Okay? But again, this is, oh, it's wrong here. I forgot to put the exponent. But anyways, the point here is that we need to define a space of functions. Okay? Is this clear? Okay. So let's now talk about loss functions. This is perhaps more intuitive. A loss function evaluates a given specific function within that space. Right? So we can have infinitely many linear functions, but some of these linear functions will be better than others at a particular task as given by this loss function L. So this is going to be the thermometer, which is going to help us measure how good the functions that we're going to look for is. And we're going to evaluate our function's edge on our data set. Some properties of the loss function. So it measures how far from the predictions of edge of x are the predictions, it's wrong here. There's no off here. Measures how far the predictions edge x of I are from the labels of examples in D. So if I take x1, for example, and give it as input to edge, this function edge is going to return me a prediction y. I want to know how far this returned y is from y1. Okay? So we can write it this way. We can say y hat equals to edge of x. So y hat is my prediction. The loss function is going to compare y hat, which is the prediction, to the real label. And it's going to measure, if you will, the distance between them. So I want to check how far my function is from predicting the real label correctly. Loss values are always positive. Right? There's no such a thing as negative loss. The minimum loss is 0. And the lower the loss, or the lower the value L of edge, the better the function edge. Okay? So, which means that a function with 0 loss correctly predicts all the labels in the data. So if you manage to find a function edge that has loss equals to 0, this means you have predicted correctly all the labels in your training data set. Don't remember, this is the data set you have access to. This doesn't mean you are doing well on unseen examples. Right? And just for practical purposes, loss functions are normally independent from the size of m. So we normally normalize them. So we're just going to divide the result. Whatever function we use, we normally divide by the size of m, which is the number of examples. Let's see some examples. Perhaps the most basic loss we can think of is called the 0-1 loss, which just returns 1 if the prediction is exactly correct, and 0 otherwise. So if I had a binary classification problem, let's say of email and spam, I would not worry much about the email part or the feature vectors, but I would have something like this: 0, 1, 0, 0, 1, 1, 1, 0. So I would have many emails in their labels. Either they are spam or not. So my 0-1 loss is going to compare the predictions of the function edge of x. So x is this email here. So I would put the x here. This would give me a prediction. If it's 1, well, it's a mistake. right? So this is going to return 0. If it correctly predicts the label, then it returns 1, right? So I'm basically counting the amount of times I made a correct prediction. If I made it correctly, 1. If I don't, 0. Okay.
You said that when they are equal, you return 1, but it's actually the opposite.
The way, yeah, that's true. It's opposite. Yeah, it's opposite because it's error, right? Yeah. We are counting error. Yeah, that's true. We are not counting hits. We are counting error. So when there is an error, yeah, if it's different, if the prediction is different than the label, then it's 1. You're right. Yeah, and it's 0 otherwise. My bad. But another very common loss function is called mean squared error or mean squared loss. There's many names for this formula. Perhaps the most common one is MSE or mean squared error. Because it's called that because we are computing the difference between the prediction, edge of x, and the real label. We are squaring it, right? Summing all of them and then taking the average. So actually, not summing and taking the average. The summation and the division there is the mean part, is taking the average. So we are summing all the error, or summing the square error, dividing by the number of examples we have. Okay, and another very similar error is the mean absolute error, that instead of summing the square difference or the square error, we just sum the absolute error, which is defined by the norm here, or the absolute value of edge of x minus y of I, right? And these are similar, but they are different, and they have different names. So these are common options for loss functions.
This last one, it's
MAE, yeah, it's also a typo. I forgot to. MAE, yeah, mean absolute error. Good catch. Okay, so these are just examples of loss functions. Okay, what time is it? Let's see. Okay, I'll probably just go over 10 minutes a little bit so we can finish this. So when we're evaluating model performance, we have to remember we have a data set D, and we can compute a loss on that data set. But what we are interested in is actually having a low error on unseen examples that are not in the data set. So given a data set D, a hypothesis space, another type of hypothesis space H, and a loss function L, we want to find a function lowercase edge in edge that minimizes the loss function L. So we would say formally that we want the edge that is the argument or the minimum argument that minimizes this function, or the minimum argument edge that minimizes this function L. Just to formalize what you're trying to do. The problem is, if we find a function edge with low loss in D, how do we know that it also has loss in new examples or unseen examples, x prime, y prime, that are not in D? Right? That's a very fair question to raise. So let's think about this for a minute. Consider the following memorizer function, and this is a valid function. Might not be a very good one, but it's a valid function. Edge of x is equals to the label y, I, if the example xi, yi is in D. So basically what I'm doing is creating a table. I actually get the data set D, and then I store the data set in a table. This is my x1, y1, And then I have x2, y2, so on and so forth until xm, ym. So this is my function. It's this table. So if you give me an example, what I'm going to do is I'm going to look for this given x here in my table. If it's there, I return the y. Okay? That's it. That's the function. So this function has 0 loss in D. Right? Because if I pick any example that is in the data set, I'm going to predict it right. But any other example that is not here, most likely I'm going to miss. So perhaps this is the worst function we can write. But it's a valid function. And it has 0 loss in the training data. And very high loss for unseen examples. Okay, so that's not what we want. We don't want this. And in fact, we call this a problem overfit. Because we are memorizing the training data, and we are not generalizing to unseen examples. Still, I haven't answered the question. Let's see how to actually do that. So, in practice, in machine learning, when we are training models and we want to evaluate their performance, we're going to take our data set D and we're going to split it in 3. So now I'm going to derivate 3 subsets. I'm going to call them DTR, DVA, and DTE, which stands for D-training, D-validation, and D-test. All of them, they are disjoint, so there can't be an example that is in here that is here. Okay? Or any example that is in the training set shouldn't be in validation or test. The same for each one of them. So they are disjoint. And what we're going to do is we're going to use the training set. Imagine we can now I think it would be easier to draw it this way. We can see it, our entire data set D, like this bar here, and we're going to split it in 3. So we collect the data. That first step there is the same. We acquire the data and we return the data set D. But then we divide it in 3. Train, validation, and test. What is cool here is that we actually know the labels for validation and test. And this is very important. We know the answer, but you're not going to look at it during training. Because we now have separated some examples for evaluation. Right? And we need this to be this way because we need the examples here and here in validation and testing to come from the same distribution as in training. So that's why we first collect all the data and then we split. Because another way would be, okay, I'm going to collect a bunch of data, train, and then stop, and then get more data and do validation and testing. Right? That's not the best approach, because you might end up having this problem of having examples here that are not in the same distribution. This can happen. In fact, nowadays with deep learning, people don't even worry much about these things because the data sets are too large. But if you're dealing with small data sets, this might hurt you. So it's easier and better to just do that. First collect your data and then split it in 3. Okay, so now we are inside that training model step. The second step of our framework is going to be divided into these smaller steps. So first, we're going to stay here in our training set. We're going to use it until we're going to train our models until we get low error according to our loss function, until we get very low error in our training set. So we stay here until our hypothesis edge has high error. And when the hypothesis edge has a high error on the training set, we call this underfit. So the model is underfitting the data. It's not having good performance on the training set. But we can repeat training here and change the model until it gets good performance on the training data. Once we are done, then we move to the validation set. Now, when you're here, you typically already have a low error on your training data, but you don't know yet, and now you're going to validate your model, and you're going to check how well it's going to perform on unseen data. But see this, if your model has high error in the validation set, you're going to come back to the training set and tweak your model again. But now you have to balance between these two. You want to have low error, training error, but also low validation error. That's what you want. And this is the key part of having a validation set. Because when you're doing this loop, you're actually specializing your model to this validation set. So you are somehow adding bias to the model. Right? So you still need a third set that you have never seen before. You've never interacted with it. And you're only going to evaluate it once, at the very end, once you are done, once you're done with this training loop here. So in other words, when you have a model that has low validation error, you're going to just report your test error. And this is done. You cannot come back anymore, ideally. Because if you do that, then the error you get here is a very good estimate of how well your model is going to perform out there on the world. Right? If you didn't have, and sometimes you don't have a validation set, that's very common, you run in the risk of, or you're having a risk of adding bias for this set here. So if you see another set that wasn't here, actually your error might be actually higher than you think. But the error here is a very good estimate of how your model is going to perform out there in the world. We're going to actually use this. You guys are going to have a lot of assignments, and in your projects you're going to actually practice these things, and then we can discuss this in the real world. This split here depends a lot on the amount of data you have. So if you have very few examples, then maybe it's actually not very practical to have a validation set. So you just say, no, I'm not going to use it. I'm just going to use a test set because there's not enough data. There's other ways you could do. You could do what we call cross-validation, which is a way to do validation even in low data set regimes. We're going to talk about this. So there is other evaluation approaches you could use. But the most general, common one is this one. Okay, so this is my last slide for today. I was planning to talk about linear regression, but I think we should stop because there's already a lot. But just before we move to our first algorithm, which is linear regression, it's important to say that if we were in a machine learning course, from now on, we would see a bunch of different machine learning algorithms. But in essence, what these algorithms do is they define a hypothesis space, and they have an optimization algorithm that finds a function within that large space. And then you will use that evaluation approach to evaluate the model. So the overall idea we already just saw in this class, this whole pipeline of getting data, training model, evaluating. This is going to be there in any of these algorithms. In this course, we're going to only talk about neural networks, which is a whole gigantic class of algorithms. There's many different approaches here. But there are other algorithms that you should study as well. but we're not going to cover in the course. We're going to cover the first two, linear regression and logistic regression, because they are linear models that are foundational or basis for neural networks, okay? And that's what we're going to talk about next class.